With this video we will start a new topic in 3456 and look at the solution of partial differential equations using numerical methods. I'm sure you all know what a partial differential equation, or a PDE, is, but just in case you don't, it's an equation that involves functions and their partial derivatives. An example is the 3D wave equation. d squared e to dt squared is equal to c squared times d squared e to dx squared, etc. So there's partial derivatives with respect to time, x, y, and z. In general, PDEs are much harder to solve analytically compared to ODEs. However, they describe many important physical phenomena important to engineering, and that's why we consider them in this unit. Many engineering applications, and applications indeed in physics, are described by second-order PDEs, so we can write the general second-order partial differential equation as a d squared u dx squared plus b d squared u dx dy, etc. And we can also use the notation where uxx equals d squared u dx squared, uxy equals d squared u dx dy, etc. So this is a very common notation, so the subscripts down here, representing derivatives. In general, the coefficients a, b, c, etc. can be functions of x and y, and this actually is important. Also important is that the coefficients a, b, and c in particular classify the equation as being one of elliptic, parabolic, or hyperbolic. So if b squared minus 4ac is less than 0, it's elliptic. If it's equal to 0, it's parabolic. If it's greater than 0, it's hyperbolic. And the reason these are important to understand is that the solution techniques we need to use to solve for elliptic, parabolic, and hyperbolic equations are different. So that's why we need to classify the equations. So elliptic equations, an example is the steady-state compressible flow for an object flying in the x direction. Phi here is a potential, and we have 1 minus the Mach number squared, d squared phi dx squared plus d squared phi dy squared is equal to 0. Potential flow, in other words, one in which the vorticity is identically 0, can be expressed by Laplace's equation, d squared phi dx squared plus d squared phi dy squared, where our velocity is equal to the gradient of the velocity potential phi. Electrostatics, where we have a similar equation now, except we have a source term on the other side, which says that the strength of the magnetic field depends on the charges inside the domain, and the electric field is given by the gradient again of this electric potential phi. Elliptic equations typically describe steady-state problems. So, for example, this standing wave across here is in a stream crossing a beach. The standing wave is governed by an elliptic PDE. Elliptic equations are often also called boundary value problems, although they are different kind of boundary value problems to the ODE boundary value problems we've been looking at previously. The reason that elliptic equations are called boundary value problems is because the boundary conditions play a significant role in the resulting solution. So if you change the boundary condition, you can often end up with a very, very different solution. The thing with elliptic equations is they require the solution of the entire domain simultaneously, and this leads to large matrix problems that need to be inverted. Parabolic equations, the quintessential parabolic equation is the heat transfer equation, dq dt is equal to kappa d squared q dx squared. There's also the same equation for chemical diffusion, d phi dt is equal to lambda d squared phi dx squared. Why are these equations parabolic? Let's go back to what we said previously about how we can define an equation. Well, we've written here everything in terms of x and y. But there's no reason why we can't write things in terms of x and t. So if we just replace y with t in this equation up here, we can see that the uxx term, in other words the a, is equal to kappa, and that the e term, this du dt, is equal to 1, that's the coefficient of the q dt term, and all of the other terms are 0, but in particular b and c are equal to 0. So if a is equal to kappa, e is equal to 1, and b and c are 0, that means that b squared minus 4ac is equal to 0. There is also, of course, multi-dimensional parabolic equations. So the multi-dimensional, three-dimensional heat equation can be written like that, where there are partial derivatives with respect to x, y, and z. And quite clearly, this form here doesn't fit into this nice description here. Regardless, you can actually show that this equation is parabolic. Problems which have time as one of the independent variables, especially when you have some kind of spatial diffusion term like this, often lead to parabolic PDEs. Boundary conditions, of course, are important with PDEs, parabolic PDEs, but they don't define the solution alone. The rate of change of the solution, in other words, this dq dt term here, depends on local gradients inside your computational domain, so it doesn't depend just on the boundary values. These problems often also lead to large matrices that must be inverted. Note that if a steady-state solution exists to a parabolic PDE, then the steady-state solution is the solution to an equivalent elliptic problem. So steady-state just means dq dt is equal to 0, and this then here is an elliptic problem. The 1D wave equation is a hyperbolic equation. It's often written as d squared e to dt squared is equal to c squared d squared e to dx squared, or perhaps sometimes with this moved across to the same side. And the wave equation obviously describes the motion of waves. In this example down here, we have a tidal bore on a river in China. You should go to the have a look at this YouTube video. It's pretty spectacular. So why is this particular equation hyperbolic? Again, going back to our definition of what the categories are equal to. Again, we replace y with t in this equation here, and we can see that a, the d squared dx squared term, has a coefficient of a that is equal to minus c squared, and that the coefficient of d squared u dt squared is just equal to 1. Therefore, b squared minus 4ac is simply equal to 4c squared, because c squared has to be greater than 0, so does 4c squared. Therefore, it's hyperbolic. And we have something similar. We can define a multi-dimensional wave equation where we now have gradients in terms of x, y, and z. So hyperbolic equations usually involve time as an independent variable, and they are often associated with the transport of some quantity, for example, the surface elevation in waves. Important for us, and we will come across this a little bit later, is that the equation d eta dt plus c d eta dx equals 0 is actually a hyperbolic equation, even though it doesn't fit within the framework that we were looking at before. Now, in order to see this, we need to do the following. So if we write this equation here as d eta dt is equal to negative c d eta dx, we can then say that our operator, d by dt, is equivalent to the operator minus c d by dx. And what I'm going to do here is I'm going to assume that c is a constant. It doesn't vary in time or space. So if we then take the derivative of this equation with respect to time, the left-hand side is d by dt of d eta dt. The right-hand side, using this expression here, can be written as minus c d by dx of minus c d eta dx, which gives us d squared eta dt squared equals c squared d squared eta dx squared, which is a hyperbolic equation according to our categorization scheme introduced earlier. Hyperbolic equations also exist wherever you have shocks. Important in general, but certainly for us in this unit here, is that the character of a PDE can change in space. Because the coefficients a and b, etc., can be functions of space, the character can be different in different parts of our solution domain. So, for example, the incompressible Navier-Stokes equations have mixed character. These terms here look like they're hyperbolic. This term, coupled with those terms there, have a character of being parabolic. And although it's not obvious, this term and those two terms there have an elliptic character. So in actual fact, the incompressible Navier-Stokes equations, depending on what part of the domain you're in, have characteristics of all three different kinds of partial differential equations.